So one of the, I want to see if there are other people joining, and for that I need to look at participants. No, we're the two here, okay. Well, great. So first of all, an interesting piece of news here, and that was, I was talking to a friend, and he said, do you know about that Intel is doing a quantum initiative? No, I didn't know. So that is where it is. They gave me the link right here. So you know what, let's do this. Let us take that link and let us put it right here. Okay. And that's the news. So maybe here, maybe we'll say news. Sorry for that. Okay, that's the link. Now, why is that interesting? Is because if Intel does it, that is different from, let's say, as Cisco does it. Cisco is a user, Intel is a maker. Now, it's a big question if they're going to make it. I'm sorry about this, but I know they are not known for great software development. And I talk about personal experience, but that's hardware. They promote it through the SDK, and they want to approach it. I looked at it, and their major approach is pretty much like the paper that I'm going to show you today. It is making this statement: look, we have hundreds and thousands and millions of programmers, and how about we teach them quantum computing? That's exactly the paper. I'll talk about it, and that's enough for the news. Closing that, if you're interested, you can look at it because it is right here. And what I should do is make it into a link. No. Okay. Now, the theory is this. I'll show you the paper, but then we will do exercises on this paper. That's the paper. That's the slides. So let's look at this link. What is interesting here is that it takes us to the LAN. It is Los Alamos National Laboratory. So it has a little bit of science fiction and a bit of, and they're talking about, you know, there's a movie about them. Well, really about Robert Oppenheimer, but that's a movie about them because he was the first director of this lab, and they were looking for a far away from all civilization place where all the scientists would hide. I think they did hide, but Russian spies found their way. So that's a very interesting story, closing that, because we'll be looking at the slides. Now the slides are right here, so I want to download the slides if I can. Very good. Maybe that is not the best way to do it, because here we have the webinar folder, and whenever you need anything out of there, that is there. So what we're doing is right clicking, and you can do the same, right clicking and saying download. Okay, once I download that, and it immediately opens, but I want to be in control. So I'm here, I'm looking at downloads here, And that's the paper. I'm putting it on the desktop and I will be presenting from there. Okay. And my plan today is this. I'll show you the interesting things out of there, but then I will offer you exercises. So I'm very grateful that you guys were with me all this time, because I feel that I was never as good as I am today. I know it sounds funny. And Bogdan, hello. And by the way, Bogdan, where are you joining from? You can tell us or type. Maybe it's from Poland. And then what's you interested in quantum computing? Yes, you want to say something?
Can you hear me?
Yes, very well.
Yeah, okay. My interest is very, very general because what I'm doing, in fact, professionally, is the overall IT strategy of the huge international bank. So
Mhm.
that's the reason for my interest. But I'm really not interested in details like clicking things, getting them down. Uh, More of my interest is the general idea how it could be utilized right now or in the future, things like that.
Good, Bogdan. Thank you very much for telling me that. And I'll keep it in mind. And hi, John, how are you?
Right.
So I'll keep it in mind because I combine both. I talk about things in general and also practical, because I believe that, yes, I understand you don't want to click, but at the same time, clicking is useful. And who is saying this? That's one of my heroes. That's Jeff Dean. Okay. Jeff Dean, the head of Google Brain. And he said, whenever you hear about the new software, you just download it and try it. There's nothing.
Okay.
You see, there's nothing that a real thing can compare to. And he is known for, as they say, lead with code. You don't have to program everything. But he does the first step with his friend Sanjay Gamawat. That's my argument. I will not insist. Don't get into my classes, because over there I do insist. Right. Thanks for telling me, though. So let's go back a little bit. We started right here, and I am putting now what we do at the top. And I was saying that somebody brought to my attention that Intel also has a quantum program. And the reason that is very interesting is because, well, they make it. Other people might be interested in how do I use it. They are interested in how do you make it. And they have published, I looked at this link, published at the SDK, that the programmer approach to this, but really they're going to do the hardware. Well, I just hope that they'll invite me to write their courses. If they do, I'll tell you more about this, because I'm ashamed to say that, yes, I'm egoistical. If people invite me to do something, then I will learn more about them. But it does seem interesting, and I'll continue with the paper, and it will tell you something about what it was. All right, now the paper. Let me put it into this mode. So my story with this paper is personal, in the sense that I was reading the Journal of Electrical Engineers, IEEE, and they showed this paper. They said, "Hey guys, at Los Alamos National Lab, that of course a big deal." They wrote the paper, and that was my first introduction into quantum algorithms. But look at how many authors. Well, I got in touch with some of them. Is that still applicable? Is that it was still applicable? Nothing goes too fast here. All right. So I said, let me do this and let me write a course according to what they say. But what caught me was the very beginning. The very beginning says, as quantum computers become available to the general public, the need has arisen to create a cohort of quantum programmers. Well, now, after a year of study and teaching and doing, I think it is an exaggeration. There is no cohort of quantum programmers. That is because, first of all, today, exactly today, what is it today? It's Friday, August 4, 2023. There is no application that is practical. And secondly, I don't think you will need a cohort of quantum programmers. So in my case, we rebranded the course, and now my course for the technical company that I'm teaching, it is called Preparing for the Future Today. that, sorry, that makes more sense. But Intel takes the same approach. Intel, where we were right here, right? Intel is also talking about preparing a cohort of quantum programmers. Well, that's another one who is taking the same approach. Now we have both, so it's a good thing to have both views. It's coming, it's just that nobody knows exactly when it will come. All right, let's continue with the paper. So, as they again state, the quantum computers are now available to the general public. Well, let's analyze that statement. How available are they? They are available on IBM. That's how I'm running my labs. The largest IBM computer is 433 qubits, I believe, and that's pretty big. How many qubits do we need for a practical application? Well, nobody knows exactly, but about 10 times more than this is probably enough. They're also thinking of how I go into millions. And you can believe that because back when they started is 2 years ago, and at this time they were playing with 5 qubits and maybe 30 qubits. So when they today show 433 qubits, that's awesome. And I would not be very much surprised. Of course, I'm not part of the development team, but still look at this scale. Now, how are they going to progress changes? Their strategy and approach changes because eventually they get into very big computers and the noise becomes very important. That's the major limiting factor. The noise is because our qubits are not bits, they're not electronics. They are photons or ions, or I think about 10, at least 10 different physical implementations. And all these things have noise. But they're thinking about parallelizing this and making it on multiple computers. So they know what they're doing. We continue. So what now you have 3 ways of looking at it, and I absolutely must draw a picture for you guys. Here is a picture. And maybe I'll do a little circle. There are 3 ways to look at quantum computing. Way number 1 is physical implementation. In other words, where are those bits? What do you make it? I think it was Richard Feynman who the first suggested quantum computing in the 60s. He said that if we want to investigate this quantum mechanics, why don't we build a computer that does it exactly? And I think he was the first genius who invented it. So you need to do it either on frozen, super frozen circuits or photons, which don't require that much freezing or any other way. And that is what people bypass. Bypass in the sense that, yes, it is important. Yes, they are somewhere, but but you programmers, you don't have to care. That's what most of the papers say. That's what they will also say. And here they will say that we will look at quantum computing, we will show how it goes, and if you want to go deeper, then that's the book for you. So that's an interesting book. I got it. I have a PDF. And that book is 20 years old, but it was extremely good when it was published 20 years ago. Then it was published again 10 years after it was first published, and it's still the classics. And I'm learning through that, and I find that my understanding improves it. So when I'm going through the paper of people from the Los Alamos National Laboratory, I am then inserting some facts out of this book. The guy, Michael Nielsen, is a young guy. For me, everybody's young. And he recorded some of the YouTube videos. They're wonderful. I do recommend them, but I'm going to tell you things out of that. So that's how we're going to progress. So there was a physical implementation, which is interesting, but no, people don't concentrate on that because that would be too much to concentrate upon. So the next level. In other words, physical implementation tells you why it works. Maybe I should put it here. Why it works. All right. That's because a quantum computer is an amazing thing. You know, in theory, it can break all encryption. It can create new encryption that will be much better than the previous one that will not be broken. It can do other very miraculous things, and it can calculate much faster than the regular computers. That's in theory. And that's because it has a different physical nature, and physical implementation is why it works. It's not another programming language. It's not anything other than it is a real stuff. And that real stuff has tremendous potential over what is called classical computers. Now, classical computers, as we know, do miracles, and they do ChatGPT, but you can go even beyond that. So that's the first level, which we skip. The next level is how do we the regular implementation? How do we draw those diagrams? That's what we're mostly doing, and that's called circuits. In other words, if you believe me that it's doing what it's doing, if you believe the first part and are willing to skip it, then the next step is how exactly I'm programming this. And this was why it works. This now is how it works. All right. And that's what we mostly do. I will be giving you a lab today, and that lab will teach you exactly how you build the circuits. But in short, this somehow works. This is exactly what you program. And it turns out that before you do any calculation, you build yourself a new computer. You don't come to the existing one. Instead, you borrow a few qubits from IBM, and as we learned today from Intel, and you create your little computer, as big or as little as your task requires. And then you tell it what to do. Tell it the operations. The operations are like no, yes. We'll look at those operations. That's the second level of what you can do. But there's a third one. Luckily, I won't show you any fourth one. So 1, 2, 3. That's the third one. And that is the math part. So if that was why it works, and that's almost philosophy, why it even works. And that is very practical how it works. Then the last one is understand. Or maybe I should say formulas, because mathematicians will tell you that formulas is exactly it. It's understanding. And that is what I will also show. So our paper, we'll talk about that part. Let me put it here. That's what Los Alamos National Laboratory is all about. Paper. Okay. That's what it will concentrate on. Now, that's the math. And the best way is this one. Well, Michael Nielsen, they like to call it Mike and Ike because there's Isaac Chuang, but maybe book. Maybe I'll say that's the Lano paper. That is the QC book. Well, and this is a stack of books. Physical implementation is, and that stack of books I even have shown you. I have them all. So it's a stack of books. And years of study in computer science and in quantum, but at least that's what it is. So what I should do, I think, is call it 3 levels of QC, quantum computing. And with that, you know, I'm very willing to talk about this, but practically we don't need it. That is what we will do today. And that is what we will do today. That is promising. Let me check who is here. You guys all have permissions to talk. And here we are going through the paper. Okay. And the major points, I made them. Quantum computing work like this. We are taking our bits, but we're not taking bits, we're taking quantum bits. And they do amazing, miraculous things because bits can only be in 2 states, 0, 1. But qubits, they can be in a different state. And to show you what they can do, I need to address those layers. I need to go back to the picture and say, that's what describes what they can do. In brief, I can tell you that what you do is you tell those qubits what you want to be done, and then you get out of the way. Because all the time that you watch them, they don't do anything. They only do your work when you disappear. That's an amazing statement, but that is true. So you set the task, then you tell it what transformations do you want to be done on those qubits, and then you get out of the picture. Then you come back and measure, and there you are, you have your results. Now, what we're doing is a very low level. I'm showing you how to form one qubit and what it means. What we need is very high level, And that is, if I had many qubits, or thousands or millions of qubits, that's what I would do to break all encryption in the world. And that is basically the plan. But that is only for those who are interested in hairy stuff. The mathematics part of it is represented by a complex vector space. Now, you may not be afraid of a vector space. A vector is just a vector, right? We know what a vector is. It's just a few numbers. But a complex vector space means that every number is a complex number. Now, raise your hand if you forgot what is a complex number. And I think you guys don't raise your hand. But a complex number is, just to remind you, is what you get if you extract the square root of -1. So we need to be writing here, okay? We said that's the basics, but we need to get out a new drawing board. And we need to say that if you take a square root of -1, SQRT of -1 equals. Now, of course, we understand the problem. If you take 2, square of 2 is 4. And if you take -2, square of 2 is also 4. So there is no such thing as a square root of -1. But imagine that there is, and call it I. Then you have a new number called I. And now you can form numbers like 3 plus 2I, right? That's a complex number. So when we talk about a vector, we're used to vectors. Every program has vectors. But when these vectors are complex, now your brain becomes a little fried. And when you have those vectors multidimensional here, then it's called a Hilbert space. Well, theoretically, it's just as easy as what came before, but practically, I think that is an interesting, that's why I called it a little bit more hairy. But it turns out that these numbers are just the right tool to represent the quantum computing systems. So if we go back to our picture, if we go back here, and now we have this, that math is exactly right. And to represent what happens to my qubits, you use math that deals with the complex numbers. Well, again, here you have to believe me that that's the fact. And I'll show you how is that. So now I'm introducing some terminology, some terms. That's how they like to represent it. But for that, you need to know what this is. This is a qubit that has the value of 0. Let's see if I have anything. Yeah, that's a qubit that has the value of 0. If we agree that we're going to represent qubits in this notation, we'll say, well, what's your real value and what's your imaginary value, right? Then 0 will be represented like this, and 1 will be represented like this, and there would be nothing special. It would still be a 0 and a 1. If you measure this qubit, then it will give you a regular bit of 1. And if you measure, 0. And if you measure this qubit, it will give you the real value of 1, and that's it. But the thing that it can be anywhere in between. It can be anywhere in between with a certain probability. Well, if we are good so far, then probability are alpha and beta. These are the probabilities, and the only condition is that a square of the first one, and those alpha and beta are real numbers. They're not well, yeah, they are complex, but that means this absolute value That means the length of the vector that is represented by this alpha. So that square plus that square is 1. Well, if you remember the equation of the circle, you remember that x plus y, x squared plus y squared is 1. So you think, that's a circle. And indeed, later on, I'll show you how you should think of it as a picture. But right now, we introduced the notation and we said that this is what we use to represent the qubit. And that is what we draw on the board if we want either to scare people away or to endear them to us, that we want to now do operations on that. But I wouldn't be scared. I would just say that, okay, I accept that there are magical things called qubits and that they can be in different states, okay? And further on, Mark, you said that you're going to do something about those qubits. Well, I'm going to do operations on this qubit. Well, I really need to go all the way to the last picture here. That's a great way to represent individual qubits, okay? You see that it's a sphere, that it can be exactly 0 right here. It can be exactly 1. It can be anything in between, and that in between gives you an enormous power of computation. That's why. So if you always keep referring to this thing, then you will remember nothing special. It's just that would be just a bit, and that's a qubit. And that is what gives me the power. So we made step number 1. We said there are some qubits. We made step number 2. There is a mathematical representation of them, but we always remember that that you can explain it. Now, there are 2 theories on that way of explaining. One is that mathematics is the queen of all science, and the physicists are lucky to be taught mathematics because it helps them do physics. But really, the kings are the mathematicians. And a different point of view is represented by Richard Feynman, the physicist, who says mathematics is just a quick way to calculate your restaurant bill. It's just operating your numbers. What really is important is physics, and physics represents reality. Mathematics is somewhere, so it's a servant to the queen, and the queen is physics. So keep both points in mind. Keep both points in mind, and that will be the representation of qubit. And from then on, I'll show you some examples. So the examples are right here, and what I will ask you to do is follow me and run it. In other words, I'll give you exercise. Now, for the exercise, I really should give you a link. So let me open that link. Okay, here. Quantum Computing Lab. Go to Pocket Guide. Okay, and go to exercises. Okay, so what you need is that link. And therefore, when I say do exercise 1, well, put a link on that exercise 1. Okay, now if you click there, you will get exactly to this place. And I will first explain it here. I'll explain you what it does. Then I will download that. The only thing is that that somehow is not complete. So what we will do, if you give me a second, I will verify why the other thing is not included, and that I can do from another computer. Now that is quite unbelievable. I don't see it there, but it should be. So please give me a second. Hey, I'm bringing this up to verify where did my favorite new exercise go. Cannot believe, but I don't see that. So that's okay. I'll prepare you exercise number 2. It is somewhere, but I'll show you what we're dealing with. Because what we're dealing with is exactly the, well, we're right here, in here, right? The math I just showed you, the physical implementation we said we are not going to look at, and so I'm showing you the circuits. And on a simple level, that is the circuit that you need to do. On a more complex level, you get thousands of the circuits and you do very complex manipulations and you end up going here. And that's where you begin to see the real algorithms. For example, this algorithm will break the encryption. This algorithm will do an amazing search. And I'm only showing two of them. So a distance from here to there, the distance from the first lab is like the distance from ABC when you're trying to spell out your first letter and writing war and peace. That would be this. So why don't we do this? Why don't we do both? And then you will appreciate the distance. Well, first we said that we're going to go here, right? That will be the very first, that's I'm spelling A, and then later on I'll show you the end of the road. Okay, now to run this, you need to click on download the raw file. Okay, I downloaded the raw file, it's my download directory, and then I'm going to column. That is mentioned in the notes, but you can always find them. So cancel this and you say upload my lab. Here you are, upload my notebook. And I just downloaded that notebook, so it should be here. And indeed it is here. All right, so I open it. Now, this is the notebook. That is how you talk to quantum computers. That's their language. And that environment is where you run a particular technology. So I remember that I want to keep the big picture in mind and the little picture. That's a little picture, every detail. And I would say it is not easy, right? But at the same time, I hope you understand why I need to keep both points of view in mind. Because without sometimes making your hands dirty, you really quite don't get it. You think you talk about and understand a little bit of what you're doing, but you don't. All right. So that is the lab. The way you run it is by clicking it here, and then it shows you what it says, the code, and then you say Shift Enter, and when you say Shift Enter, it runs. So we are drawing a circuit. Now, what is this? The very first simplest possible operation on the qubit is to say no, negate it. That's denoted by X right here, X. And the very first exercise that I'm suggesting that you do is this. Well, what happens if you negate a thing twice, right? What happens minus minus? Well, obviously minus minus is a plus. If you negate it twice in classical math, you get one. Well, that's exactly what I'm trying to do. So I'm trying to come here and run it, but it assumes that you have already installed the library Qiskit. So if I run it here like this, then it will try to run it. You see, it's trying to run it, but it should error out because it will say, haha, you don't have Qiskit installed. Well, haha, I prepared the solution. I said, but install it like this. That's because in my local environment, I would just install it and it would work. And after that, I would never have to install it. But if I am on Colab, I am coming into a fresh environment every time. Maybe there is a way pre-install on Colab, like packages on Colab. Let's see if there is a way to do this. How install Python packages on Google Colab. I want to pre-install them and never have to install it again. But it says you still need to install. So I think there is no way, but that you may research. But it's okay. Well, while I entertain you with this conversation, it did install, it imported this, and now I'm saying, hey, Qubit, negate yourself. All right, that means say a no. Now, where did I get this qubit? It was right here. I said quantum circuit. Oh, simply one qubit. What is this one? This is additional bit. So I'm going to do something to this qubit and then measure it by putting it into one. All right, you couldn't go much simpler than that. And I'm interested in first negating that and then negating it again. So I'm taking the first denoted by 0 qubit and making it into a no, and then again a no. What I should get is the same as I had, right? And that I do, first of all, by drawing what I have asked it to do. I've asked it to take the qubit, number 0, and negate it twice, get back the result, and then I want to measure. By the way, those pictures don't look the same because in Colab, it is a different library to draw things, but you can realize that these are the same. Okay, not so beautiful in Colab, much better on my environment, but it does mean the same. And now I want to draw the result. Okay, so show me the result. And the result will be 0. So if I started with 0, then after 2 negations, it became 1, and then back to 0. I know that's not quite an amazing thing, but then again, when the child writes his first letter or her first letter, that's not very amazing. What is amazing is that we understand where you go from here, you go to the moon, all right? So here's what you need to do. You need to do exactly what I've done. You need to go to Colab, upload this, run it there, and understand what I have done. I have said no 2 times. It became yes. So if we go back to this picture, okay, then we looked really at 2 implementations. To close the circuit, we just need to talk about, okay, in the real world, it won't be 1 qubit, it will be millions. And what do I do with them? Okay, I think I showed you what I wanted to show you, and I mentioned that, well, just multiply it by a million. But now is a good time for questions, and I will stop presenting. All right. Because sometimes it helps when you stop talking and stop showing. Okay, no questions, guys. You're not alone. I was the same a year ago. First, I couldn't believe that quantum computing really exists. Then I couldn't believe that it's so complex and it has all these three levels. Now I kind of believe it because of the price, and the price I think is like $3 a second. You would believe that. And I kind of believe it because so many smart people pretend that they understand it. Even though if you don't understand it, you can use Richard Feynman on your side, because after he received the Nobel Prize, he says, well, guys, you don't understand what I'm saying, and my students don't, even after 4 years. And that's because the teacher doesn't understand, and that's because nobody understands. So that is the last thing that I will leave you with. And for that, maybe I'll just go to YouTube and get you his lecture right here. That's a wonderful lecture. So let us open it in a new tab. Okay. So I close that. I go back to our record and I say this. Don't understand. Richard Feynman. It's uppercase. Even that. Wow. Really? Yes, with a Y. Okay. Does not either. And here's the link for that. All right. Well, that's pretty much it. Next time we'll continue in the same vein, and you tell me if that level is good, because I'm jumping all the time between a little level of bits and the high level of what does it really mean. All right, so good. I see you next time, I hope, and you be well and have a great week.
Thanks very much. Same to you. Bye.
Goodbye.